Welcome to part 1 of my course on Algebraic Foundations. Part 1 will be about algebraic structures called groups, and in the first chapter I will simply introduce them and discuss the definition and some basic properties. We will begin by studying some examples to motivate the notion of a group. Then I will give you the definition of a group and study some of their properties, and third we will look at subgroups, that is, groups within other groups. First, let's look at the motivating examples. And we begin with a very well familiar one, the integer numbers z. Algebra is about understanding the processes of computations. This means what are the objects of computation and which laws have to hold to formulate equations and solve them. Our first example, and you could think of this as the most fundamental example to explore these algebraic questions, are the integer numbers that you're well familiar with. Z is the set of numbers 0, 1, 2, 3, 4, 5, 6, 7, and so on up to infinity, and the negatives -1, -2, -3, all the way down to -infinity. And this set and these numbers here we consider together with their addition now. And we will ignore multiplication at the moment and come back to this at some later point. But for now, we just focus on the addition of the integer numbers. What does it mean to add two integer numbers? You know this notation here, x plus y. So this is precisely speaking a map plus from the Cartesian product of the integers with itself. So you take a pair of integers, and what you get out from this map is a single integer that we denote by x plus y. And instead of using the usual functional notation plus with arguments x, y, we stick with our familiar notation x plus y for this map. There are two laws for this addition that you're probably very well familiar with. First is the associativity. So if we add three integers, then it doesn't really matter whether we add x to the sum of y plus z, or if we add x plus y first and then add z later. And the other familiar property is commutativity, which means that the order of the operands doesn't matter in the addition. So x plus y is the same as y plus x. We have one element in the integers that plays a very special role for the addition, and that's the element 0. So why is this special? Because it's the only element that leaves all the other elements unchanged under addition. So for any integer x, we have x plus 0 is equal to the original x. And because of this property, we call 0 the neutral element with respect to the addition in the integers. Another operation that we have is subtraction. So given two integers x, y, we can form x minus y, so we subtract y from x. But if we think about it, then subtraction is nothing else but adding integer x to the negative of the integer y. So recall, for each integer y, we also have its negative included in z. So subtraction is nothing but adding x to the negative of some other integer. And this reminds us of this important property that I just stated. For every integer x in z, there exists its inverse element, inverse here with respect to the addition, which is called minus x. So that's simply the negative number of x. And this inverse is defined by x minus x equal to 0. So if we add x to its inverse element minus x, we get the neutral element 0. And note that talking about the inverses, the negative elements, only makes sense after we establish the presence of the neutral element. Okay, so if we didn't have the element 0 in the integers, then it wouldn't make sense to talk about negative elements. There's another special element in the integers, which is the element 1. And the 1 is special because we can use it to generate every integer by repeatedly adding it to itself, or taking its negative minus 1 if we want to generate the negative numbers. So for any integer x, we can obtain it by taking 1 and adding it x times to itself. Or well, if it's a negative integer, we would use the absolute value of x times minus 1. Maybe curious why we even emphasize these properties so much because they're well known to us, they're very well familiar. But I do this because we will see that these properties that we just listed for the integers reappear in completely different objects. And because these properties reappear, it will allow us to develop a very powerful common theory for all of these different objects. And this brings me to our next example, the permutations. So at first glance, permutations are something completely different from integer numbers. Namely, a permutation sigma of some set x is nothing else but a bijective map sigma from x to itself. Now recall from set theory that a bijective map is one where there's a unique correspondence between elements in the input set to every element in the output set. So we in particular have an inverse map that reverses this sigma. And here a permutation is the bijective map from one set to itself. And we focus here on finite sets, and because in finite sets we can just enumerate all the elements, we just stick for simplicity with elements, with the sets that have the elements numbers 1 to n. So I denote this set by xn. So this is the set of the numbers from 1 to n for some integer greater or equal to 1. And for these sets we can interpret the permutations as rearrangements of the numbers 1 to n. And we use the following notation for them. So a permutation of such a set from 1 to n is written like that. In the top row, we just write the numbers 1, 2, 3, blah, blah, and so on up to n. And in the bottom row, we write the images under this permutation. So here we state with which element they have been exchanged. As an example, let's look at the permutation sigma for the set 1, 2, 3 that assigns 1 to the element 3, 2 to itself, so nothing changes for 2, and 3 is assigned to the element 1. In this notation we would write sigma as 1, 2, 3 in the top row, and then 3 to 1, so the 3 here is because 1 gets assigned to 3, the 2 here because 2 is fixed, nothing happens with the 2, and the 1 here because 3 gets assigned to 1. So what this permutation does is it just swaps the position of 1 and 3 and does nothing to the element 2. And for the permutations of the numbers 1 to n, we denote the set of all permutations by this letter Sn. This is a finite set, as you may know from combinatorics, because we know that the number of all permutations of n elements is n factorial. So the number of elements in this set Sn is n factorial, which by definition is n times n minus 1 times n minus 2 down to times 2 times 1. And you can actually quickly derive this formula by thinking about how you can enumerate all the permutations of n elements. So if we stick to this notation here, you would have n choices to pick the first entry here. After you fix the first entry, you would be left with n minus 1 candidates to pick the second entry. After you fix the first 2, you would be left with n minus 2 entries for the third, and so on, down to the last element. So once you've fixed all the images for 1 up down to n minus 1, you would only have one element left that you could map n to. And this corresponds to this final factor 1 here. So yeah, thinking about it like that, you can easily derive this formula here. Two permutations are both maps from the set xn to itself. And this means we can compose them to obtain a new permutation. So in the usual notation of map compositions, sigma composed with tau, if these are two permutations, is again a permutation from xn to xn. And by definition, this is just the permutation that takes the number k and first permutes it by tau, and then the result of that is permuted by sigma. Okay, so first we rearrange the numbers 1 to n according to tau, and then we take the rearranged numbers and again rearrange them according to the permutation sigma. Schematically, we can see this in this little example here. So sigma is the permutation that maps 1 to 2, 2 to 4, 3 to 1, and 4 to 3. Whereas tau is the permutation that fixes the element 1, maps 2 to 3, 3 to 4, and 4 to 2. And you can verify that the composition of these two, where you apply tau first and then sigma, is this permutation here. And to make it a bit easier to derive this, we can write down the two permutations like this. So the first one in the composition, the rightmost one, is tau. We apply this first using these rules here, so I indicated with these little arrows. 1 is fixed, so 1 gets mapped to 2. 2 goes to 3. 3 goes to 4. And 4 goes to 2. And after we're done with that, we apply the permutation sigma. And with sigma, 1 goes to 2. 2 goes to 4. 3 goes to 1. 4 goes to 3. And to get the composed permutation of those two, we simply follow those arrows. 1 goes to 1, goes to 2. So 1 goes to 2. 2 goes to 3, goes to 1. So 2 goes to 1. 3 goes to 4, goes to 3. So nothing happens with the 3 after all. It's fixed. 4 goes to 2, goes to 4. And same for element 4. It's fixed. It's mapped to itself. And in this way you can see that this is indeed the composition of those two permutations. And together with this composition, the set Sn of all permutations of n numbers becomes an algebraic object itself. These permutations, together with their composition, share a few properties with the integers z. Firstly, the composition is associative simply because it's a composition of maps, and composition of maps are always associative. So if you compose rho with the composition of sigma and tau, it's the same as if you take the composition of rho and sigma and compose it with tau. That's just a standard property of maps, so nothing particular about permutations gives you this associativity property, but it's just because permutations are maps. Then we also have a neutral element for this composition, just like 0 was the neutral element for the addition in Z. And this neutral element is the identity map of the set of the numbers from 1 to n. So the identity map is simply the permutation that keeps all the numbers in their proper original order. So it doesn't rearrange them at all. And the identity map obviously satisfies this neutral element property. If you compose any permutation with the identity, that's like rearranging a set of numbers after, well, not doing anything to it. That's the same as just applying sigma. And it's the same as first applying sigma and then not doing anything with it. And since the permutations are bijective maps, which means they do have inverse maps, so invertible maps, and the inverse maps are also invertible due to the bijectivity, the inverses are also permutations. So this means that for every permutation sigma, there exists its inverse permutation sigma to the -1. So this is just the inverse map in the regular sense of mappings. And of course, sigma combined with its inverse is by definition the identity, and it's the same as combining the inverse with sigma from the left. So these properties make the permutations similar to the integers, but there are also some differences. And the integers satisfy the law of commutativity, but for the permutations, beginning with number n greater or equal to 3, commutativity does not hold in general for permutations. Let's look at this example here. We have sigma, the permutation mapping 1 to 3, 2 to 1, and 3 to 2, and tau, the permutation that swaps 1 and 2 and fixes the element 3. And if we compose them, if we compose sigma after tau, we get the permutation 1 to 1, 2 to 3, and 3 to 2, so the permutation that swaps 2 and 3. But if we compose them the other way around, first apply sigma and then tau, we get the permutation that fixes 2 and swaps the other elements, so the one that swaps 3 and 1. And clearly these two are not the same. So here, with respect to the composition of permutations, we do not have commutativity. And you can easily extend these permutations here to permutations of any number larger than 3. So this example also holds in, for larger numbers 3. And we see that for any n greater or equal 3, the permutation set with the composition is not commutative. Also, Z was generated by a single element, 1, through repeated addition of this element. But for the permutations, we usually cannot do with just one generating element. For example, if we just stick with S3, so the permutation of 3 numbers, then the set of permutations is generated by these 3 permutations here. The one that swaps 2 and 3, the one that swaps 1 and 2, and the one that swaps 3 and 1. And it's a general but very non-trivial result that the permutations on n elements are generated by the so-called transpositions. So these are those permutations of the numbers 1 to n that swap precisely 2 elements and leave all others in their place. So you can see these are all transpositions. They all fix one element and just swap the other 2. And this is a principle that holds in general for any number n. But as I said, it's not a trivial result. I will just state it here, but not prove it at this moment. But be sure we will get back later to this. Now on to our next example, something different. Here we look at the symmetries of a circle. Just consider any circle located in the plane, and by symmetry of the circle we mean any transformation that maps the circle to itself. So mapping a circle to itself means every point on the circle is transformed to another point on the circle. And these transformations are any rotation r alpha about the center of the circle by an angle alpha, and any reflection sigma L about an axis L passing through the center of the circle. Other transformations are not symmetries because they will move the circle or distort the circle in a way that some of its points will be moved outside the original circle. Here we have an image to illustrate this. So here's our circle, here's the center, here's a point P on the circle and the vector pointing from the center to this point P. And we can extend all of these rotations and reflections to transformations of the whole plane. Then they would be linear maps when we do this. And from now on we shall assume that we do this. And if you want to learn more about them, for example, their matrix representations and some of their geometric properties, I recommend you watch my course on the MathFlix channel, Linear Algebra in 2D. But let's have a look at how they work now. So here we have the rotation by an angle alpha, which simply takes this point P and rotates it. So the rotation doesn't change the distance to the center, so it's kept on the same circle, just at a different angle alpha to its original position. And a reflection across such an axis L that runs through the center of the circle, does what it says, it reflects it. So we take the perpendicular line to this axis and draw it from the point P to the other side until we hit the circle again, and this is the reflected image of P under this reflection sigma L. Now we use the notation sim circle to denote all the symmetries of the circle, so the rotations and the reflections. And once again we can observe some similarities between this set and our integer numbers or our set of permutations Sn. Namely, these symmetries in sim circle are maps of the plane to itself, so we can actually compose them. And the composition of two rotations, r alpha composed with r beta, is again a rotation by the angle alpha plus beta. That makes sense. You first rotate by an angle beta and then you rotate by an angle alpha. That's exactly the same as if you had rotated once by the combined angle. Now, which may not be so obvious, but in fact is true, that if you compose two reflections, let's say sigma L and sigma H, across axes L and H, then what you get is a rotation r to alpha, so by twice the angle alpha that is enclosed between the two axes L and H. And again, what might not be so obvious, if you compose a rotation and a reflection, say r alpha and sigma L, then you get again a reflection, sigma H, and here the axis for the reflection is our original axis L, rotated by the angle 1/2 times alpha, so where alpha is the angle here. And if you compose them the other way around, sigma L composed with r alpha then you get again a reflection, sigma h prime, and here the axis h prime is the original axis L rotated in the opposite direction, so by minus 1/2 times alpha. In this way, we find that the composition of symmetries yields again other symmetries of the circle. So composition is an algebraic operation on the set sim circle, on the set of symmetries of our circle. Now let's compare this to the integers or to the permutation. And the first thing we notice again is that since the elements of sim circle are maps of the plane to itself, or by restriction of the circle to itself, their composition is associative. Here we have the associativity property again, and just as I said for the permutations, this is simply a property of maps. This has nothing to do with this circle in particular, but all composition of maps are associative if you're allowed to compose the maps in the first place. There's again a neutral element in the symmetries of the circle, and it's the identity map again. Now this time it's not the identity map of a finite set of numbers, but it's the identity map of the plane, which clearly maps the circle to itself because it fixes every single point on it. And we have inverses for all the symmetries of the circle. Namely, every reflection is its own inverse. If you think about it, that's pretty obvious. If you take a reflection axis and you reflect about it, and then you do the same reflection again, everything is just back to where it started. So composing a reflection with itself gives you the identity map. And for every rotation, we can undo the rotation by simply doing the rotation by the same angle but in the opposite direction. So R alpha composed with R minus alpha is R0, rotation by angle 0, and if you rotate by nothing, then you simply have the identity map again. So this shows you that we do have inverses for all the symmetries if the identity map is the neutral element of our set of symmetries. The set of symmetries of the circle is an infinite set, since we have a rotation and a reflection for each angle alpha between 0 and 2 pi. Now, this set is even larger than the integers, so recall the integers were also an infinite set, but the integers are countable, whereas this interval from 0 to 2 pi is not a countable set. So this shows the symmetries of the circle are significantly larger than the set Z. Let's look at commutativity. First, we observe that all the rotations commute, because rotating by beta and then alpha is the same as rotating once by alpha plus beta. So R alpha composed with R beta is R alpha plus beta, but addition is commutative, so this is R beta plus R alpha, which is the same as R beta composed with R alpha. So the rotations commute among each other, but reflections do not commute, and also reflections and rotations do not commute in general. For example, if we look at this here, R alpha composed with sigma L, the reflection across L, composed with R minus alpha is sigma H. And here H is the line obtained by L by rotating it by an angle alpha. Now, if R alpha and sigma L would commute, this would imply that L is equal to H, because then we could move the R alpha past the sigma L here, and then it would cancel out with this one, and we would be left with sigma L. But if H is the line obtained by L by rotating it by an angle alpha, then L equal to H can only be the case for alpha equal to 0. And this shows that we do not have commutativity in general when it comes to mixing reflections and rotations. So the whole set of symmetries of the circle, together with the composition of symmetries, is not commutative, even though the rotations actually are commutative among themselves. Also, when we look for generators of this symmetry set here, recall we had the 1 as the convenient generator for Z, and we had finite number of generators for the finite set Sn. But we cannot write it down that easily for these symmetries here. And this is due to the uncountability of this set. So if we wanted to write down a minimal set of generators, that would be very difficult. Of course, we could take the whole set itself as generators, but that would be a bit silly because it wouldn't give us any interesting information. One thing we can say is that the set of all reflections would be enough to generate this set of symmetries, or the set consisting of all rotations together with one single reflection would also be enough to generate this set of symmetries. So these are still not minimal sets of generators, but at least it's an interesting information on much smaller sets that would be enough to generate all the symmetries. Now we come to our next example, which in a way is similar to the previous one because it's derived from that. Here we look at the symmetries of an equilateral triangle whose vertices lie on the circle that we just studied before. So we have this situation, we have our circle again, here the center, and then we have 3 points on the circle that are arranged in such a way that they form an equilateral triangle. And for convenience, we just label the vertices 1, 2, and 3. Here we write sim triangle to denote the set of all transformations of this triangle to itself, so the symmetries of the triangle. And we note that we can identify any transformation of this triangle with the transformation of the whole plane that maps the circle to itself, because the endpoints here lie on the circle, so any transformation that maps the triangle to itself corresponds to one transformation that maps the circle to itself. And in this way, we may consider the set of symmetries of the triangle as a proper subset of the symmetries of the circle. But it is a much smaller subset than the full symmetries of the circle, because not every rotation or every reflection will preserve this red triangle here. And in fact, the inner angles of this equilateral triangle are 120 degrees, so that's 2 pi divided by 3. And the symmetries of this triangle are the following rotations and reflections. It's only 6 of them, so much less than for the full circle. First, rotation by angle 0, which is nothing else but the identity map, so the one that doesn't do anything. It's obviously a symmetry. Then we have the rotation by 2 pi divided by 3, so this is a 1/3 of a full rotation. This is what's happening here, so 1 gets rotated where the 2 was before, 2 gets rotated down here where the 3 used to be, and 3 gets rotated here where the 1 used to be. The next is if we apply this twice, we get a 2/3 rotation, which is the rotation by angle 4 pi divided by 3. This is this one here, where 1 gets rotated to where 3 used to be, 2 gets rotated to where 1 used to be, and 3 gets rotated to where the 2 used to be. Then we have reflections, sigma L0, L1, and L2, where Lk is the axis enclosing the angle 2k times pi over 3 with this x-axis here. So sigma L0, it's angle 0 with the x-axis, so it's just a reflection across the x-axis that fixes point 1 but exchanges the points 2 and 3. Next we have the reflection by angle 2 pi over 3. That would be this axis here, the blue one. That one fixes point 3 because it's right on the axis, and it switches the points 1 and 2 of the triangle. And finally we have the rotation sigma L2 by 4 pi over 3, the angle of the axis with the x-axis. This one fixes the point 2, the vertex 2 of the triangle, and flips vertices 1 and 3 of the triangle. So the symmetries of the triangle form a finite subset with only 6 elements of the uncountably infinite set that makes up the symmetries of the circle. Again, we have associativity of the composition of symmetries because this is just inherited from the larger set symmetries of the circle. And the composition of 2 symmetries of the triangle is again a symmetry of the triangle. We have the neutral element, the identity, within the symmetries, which we just saw before. And every symmetry has an inverse within the set of symmetries of the triangle. So for the rotation 2 pi over 3, the inverse is just 4 pi over 3. So we have a 1/3 rotation combined with a 2/3 rotation. We get the full rotation, which is the same as not doing anything if we rotate once by 2 pi. And of course then the inverse of this one is this one. And for the reflections, again, we simply have the property that each reflection is its own inverse. So reflecting twice across the same axis is as good as not doing anything. Another interesting observation is that every symmetry of the triangle is completely determined by where it maps the vertices 1, 2, 3. Therefore, we can interpret symmetries of this triangle as simply permutations of the set 1, 2, 3. And in fact, the number of elements of the symmetries of the triangle is 6, which is 3 factorial. So it's the same as the number of symmetries of this set here, of the set of 3 numbers. So we can identify the symmetries of the triangle with the full set of permutations of the numbers 1, 2, 3. And here we make this explicit, so the identity obviously is identified with the identity permutation. The 1/3 rotation, so rotation by angle 2 pi over 3, is identified with this permutation here. 1 goes to 2, 2 goes to 3, 3 goes to 1. The 2/3 rotation is identified with this rotation. 1 goes to 3, 2 goes to 1, 3 goes to 2. And the reflections are identified with these 3 permutations here that each fix one element and swap the other 2. So here the 1 is fixed, the other 2 are swapped. Here the 2 is fixed and the other 2 are swapped. And here the 3 is fixed and the other 2 are swapped. And this shows us that the symmetries of the triangle and the permutations of 3 elements actually have the same algebraic structure, even though they appear in completely different contexts. So the sets they act on are completely different. So once it's the triangle and the other one is just a set with 3 numbers. But we've seen that this triangle is in a way sufficiently rigid that we can completely reduce its symmetries to the permutations of these 3 numbers. And that's a very interesting observation, that identical algebraic structures may appear in completely different contexts. Now we're ready to get the definition of a group. So the properties we just studied for the integers, the permutations or the symmetries of a circle or a triangle will be distilled into the following definition. A group is a set G together with an operation called circle that takes 2 elements of G, produces a new element of G that has the following properties. First, the operation is associative, which means that if we have 3 elements, G1, G2, G3, from the set G, we have that G1 composed with the composition of G2 and G3 is the same as the composition of G1 and G2 composed with G3. Second, there exists a neutral element, also called the identity, which is customarily denoted by the letter E, that satisfies for all elements G from the set big G, that G composed with E equals G, and this is the same as E composed with G from the other side. And thirdly, every element G has an inverse element written like this, G inverse, that satisfies G composed with G inverse is the neutral element, and this is the same as G inverse composed with G as well. And such a group is called abelian, after the Norwegian mathematician Niels Henrik Abel, or also called a commutative group, if for all elements G1, G2 from our group, the order of operation doesn't matter. So if G1 composed G2 equals G2 composed G1. And a few remarks on the notation so you don't get confused in this course or when you read up in the literature. Strictly speaking, a group is a pair of 2 things, namely first a set G and second the operation on this set. And I will use this pair notation when it's important to emphasize the operation here, but very often I will write simply G to represent the group when it's clear from the context which operation we mean, or if it simply doesn't matter which operation we mean. And usually the group operation is simply written like a multiplication, so G1.G2 or simply G1, G2 without any symbol here for the operation. And this is the case mainly when we do not make any assumption on whether the group G is abelian or not. And then the neutral element is often also denoted by the symbol 1 or sometimes 1 index G to emphasize which group we're looking at. And since we write it multiplicatively, we also use this power notation, G square for G times G, G3 for G times G, and so on. When we're looking at abelian groups, we usually write them additively. That is, we use the symbol plus for the operation on the group. And this is done to suggest a similarity with the abelian group of the integers z with plus, with the addition. And here the neutral element will be denoted by 0, again in similarity to the integers. And instead of using a power notation here, we use a multiple notation. So we write 2g when we mean g plus g, we write 3g when we mean g plus g plus g, and so on. And when we use more exotic symbols for the group operations, like all kinds of stars or dots or bullets, then we do this to emphasize that we are talking about some abstract group and we do not want to associate it with any particular well-known group in our heads. Time to look at some examples. Well, let's just quickly revisit our previous examples. So the integers z with the usual addition are a group, which we saw in the beginning, and they're even an abelian group because the addition is commutative. And when we speak of the group z, it is always implied that the operation is the usual addition. So we will just talk about z as a group without explicitly stating which operation we mean, and then it's understood that we're talking about the usual addition. Example 4, our permutations Sn of the set of numbers 1 to n with the composition of maps is a group. And as we saw, for n greater or equal 3, this group is not abelian because not all permutations commute with one another. The symmetries of the circle with the composition of maps is a group. Again, not an abelian group. And the symmetries of the equilateral triangle with the composition of maps is a group. And this was a group contained in the larger group from the previous example, the group of symmetries of the circle. And an interesting thing to notice here is that these three examples, the permutations and the two symmetry sets, are defined through their action on some set. So here the permutations act on the set of numbers 1 to n, the symmetries act on the circle, or here the symmetries act on the triangle. So there's always some additional set that we use to define these groups. But in the definition of the group that we just gave, these acted on sets do no longer play a role. So when we're talking about groups, we focus on the properties and the laws that are intrinsic to the acting elements, that are intrinsic to the symmetries or the permutations here, but we do not care so much about the sets that the action takes place on. We care about the algebra of the acting entities here. These form the groups. And I think it's always helpful if we learn about a new structure to understand when such a structure does not appear. So let's look at some examples of non-groups. Here we take a subset of the integers, which I call x, which contains the integers from -4 up to +4. And together with the addition, this inherits the associativity of the integer addition. We have the neutral element 0, and every element in here has an inverse element. So for every positive number, we have the corresponding negative number. Still, this is not a group. Why is that? Because the addition plus is not a proper operation on the set x. And we see this easily if we take the element 4 and add it to itself, then we get the number 8. But 8 is not contained in x. So addition is not an operation on x. We would have to leave the set x to get all the results for the additions, and this means this pair x and the addition of integers is not a group. We also say that x is not closed under the addition. The next example, let's look again at the integers, but now we look at the multiplication. And together with the multiplication, the integers are not a group. Why is that? Clearly, the multiplication is an associative operation on z, and we have a neutral element, namely the element 1. So if we multiply anything by 1, we get the same element again. But what we're missing are the inverses of elements in z. So for any element that's different from ±1, we do not have an inverse in z because, well, the least we would have to do is to introduce fractions. But fractions for elements other than ±1 are not contained in z. So we do not have inverses for the multiplication. But even if we introduce fractions, it still doesn't quite work out. So if we look at the rational numbers q, so basically taking z and filling it up with all the fractions, or even the real numbers r together with the multiplications, they're still not groups. Clearly, again, multiplication is associative. we have a neutral element, but still we have the element 0 that does not have an inverse for the multiplication. So recall, you're not allowed to divide by 0, and so there's no way to define a proper inverse element for 0 within the rational or the real numbers with respect to the multiplication. And this means Q and R are not groups with the multiplication. But let's look at some additional positive example of groups. So we've seen that Z with the addition is a group, and in exactly the same way we can convince ourselves that the rational numbers with the addition, the real numbers with the addition, and even the complex numbers with the addition are groups. And to vindicate the multiplication a little bit, well, let's use this letter hollow K to denote either the rational numbers, the real numbers, or the complex numbers. And as we just saw on the previous slide, K is not a group for the multiplication, but we can define a subset, which I call K times, with this symbol here, which is meant to be all element x of K, such that x has a multiplicative inverse 1 over x. And for these three here, this is the same as simply taking K without 0, because every element in either of these sets that is different from 0 does have a multiplicative inverse element 1 over x. And then, indeed, this K times becomes a group, since any product of non-zero numbers in K again yields a non-zero number, so this is closed under the multiplication. It's associative, we have the neutral element 1, and the inverses exist by definition here. So that makes it a group. And a more complex example here, again, K is either of the rational, the real, or the complex numbers. And by K to the n times n, we mean the set of n by n matrices with coefficients in K. Now we observe the following for the n by n matrices, and here you probably need some knowledge from linear algebra. So if you're not familiar with linear algebra at all, feel free to completely ignore this example, or maybe feel motivated to look it up somewhere. But the multiplication of two n by n matrices AB again yields an n by n matrix, A times B. So it's closed under multiplication. Matrix multiplication is associative, so A times parenthesis BC is the same as parenthesis AB times C. To prove this is quite tedious, so I'm not going to do it here, but it's essentially done by just writing out the formula for the matrix product coefficient-wise. But the n by n matrices do not form a group for its multiplication for a similar reason that we had for the sets K. It's simply the fact that many matrices do not have an inverse with regard to the multiplication of matrices, and these are precisely those matrices whose determinant is 0. Okay, so if you're familiar with linear algebra, you've probably seen this. It's a famous result. The determinant of a matrix is 0 if and only if this matrix is not invertible. But we can define this set here, which is called GLN of K, which consists of those n by n matrices whose determinant is different from 0. And this subset of the n by n matrices is called the general linear group over K. So that's GL, general linear group. And the name already tells you it is a group. Let's quickly check this. So associativity we have that it's closed here. So from the well-known formula for determinants, the multiplicativity of the determinant, we have that determinant of A times B is the same as determinant of A times determinant of B. So if these two determinants here are different from 0, then of course the determinant of the product will be different from 0 as well. And this shows us that the product of two elements AB in this general linear group is again an element in the general linear group, so that's good. We have a neutral element, namely the identity matrix, so which is the matrix which has 1 on the diagonal and 0 everywhere else. It has determinant 1, so it's clearly contained in GLNK. And for every element in GLNK, we also have that its inverse matrix is contained in GLNK. So first we know the inverse exists because this is equivalent to the determinant being different from 0. And the determinant of the inverse is just 1 over the determinant of A. And if this is different from 0, then of course the inverse also has a determinant different from 0. So the inverse is also contained in GLNK, and this shows that indeed the general linear group is a group with the matrix multiplication as operation. And here's an exercise for you to check whether these three are groups. So pause the video for a while and look at these three examples. G1 is a subset of the permutation group on n numbers. So these are all the permutations that fix the number 1. So sigma of 1 equals 1. And we use as operation again the composition of permutations. Second example is very similar, G2. These are the permutations on numbers 1 to n that move the number 1 to the number 2. And the third example, here we take R3, so the vector space in 3 dimensions. And here we have a vector cross product. You may or may not be familiar with that, which is multiplication of 2 vectors in 3 space, giving another vector in 3 space, and it's defined by this formula. So if you're not familiar with the cross product, the vector cross product, just take this formula here as its definition, and please check if these 3 are groups, or if they're not groups, or which ones are groups and which ones aren't. So here's the solution. For the first example, we know that the composition is associative, so we don't have to prove this. The identity, so the neutral element, satisfies that it maps number 1 to number 1, so that's good. It's contained in G1. And if we have a permutation in G1, then let's look at the inverse of this permutation. What does it do to 1? Well, because sigma is contained in G1, we can write this element 1 as sigma of 1 due to this property here. So we have sigma inverse of 1 is the same as sigma inverse of sigma of 1, but sigma inverse and sigma cancel out. So this means sigma inverse of 1 equals 1. And this means that sigma inverse is also contained in G1. And this makes G1 a group. But it's different with G2. This is not a group because the identity does not satisfy identity of 1 equal to 2. So the neutral element is not contained in G2, and there's no other neutral element for the composition, so this makes it impossible for G2 to be a group. And for G3, we also find that it's not a group because the vector product is not associative, which you can verify with this simple example here. So we take some standard vectors, 1, 0, 0 times, and now we first multiply out these two, 1, 0, 0 times 0, 1, 0, and then take this and multiply it from the right with that one. After that's all done, using this formula here, we find that this is 0 minus 1, 0. But if we move the parentheses to multiply these two first, then this product here gives 0. So the cross product of a vector with itself is always 0. So this gives 0, and 0 times any vector gives the 0 vector. So we have some non-zero vector, and here we have the 0 vector, so they cannot possibly be identical. And this shows that the associativity law does not hold for the vector product. And in addition, there's no neutral element and there are no inverses, but it already fails with the associativity. A quick word on generators. So recall that from our initial examples, we had some elements that generated these groups. For example, Z was generated by the number 1. By repeatedly adding 1 to itself, we could obtain any element in Z, or repeatedly adding minus 1 to itself. And the group S3 was generated by 3 particular permutations. So the general question to ask here would be, is there some subset X of our group G, such that every group element can be written as a product G equals G1, G2, Gk, of elements that are contained in this set X. So this would be our generating set then. And this is indeed a very interesting and important question in group theory, but I do not want to discuss this here. I will rather postpone it to a later chapter of this course where we will look at it in more detail. Now let's derive some basic properties of group. We are done with the definition and the initial examples, so time to prove something. First, product group. So if we have 2 groups, how can we construct a new group? And this is a very simple example. So let's say we have G1 with this circle as operation and G2 with the bullet as an operation, and these are 2 groups. Then we can look at the Cartesian product of the sets G1 and G2 and make this into a group with an operation, let's call it star, given by the component-wise operation of the original group. So the pair G1, G2 with G1 coming from this one and G2 coming from this one, operating with the pair H1, H2 with H1 coming from G1 and H2 coming from G2, is simply defined by applying the individual group operations component-wise. So we define this to be G1 circle H1 and in the second component G2 bullet H2. And the proof is probably the most boring proof in all of group theory. So all the group properties are inherited component-wise from G1 and G2. So I'm not going to spend much time explaining this. I will simply show you the equations, and if you feel like it, you can follow along and verify them. So to verify that it is indeed an operation on the Cartesian product, check that it's an operation component-wise. Yes, it is, because we assume these two to be groups already. Same for the associativity. It's a bit much to simply write down, but in the end it's just checking that component-wise associativity holds, which is the case because these two are groups to begin with. The neutral element is simply given by taking the pair which consists of the neutral element for the first group and the neutral element for the second group. And same for the inverses. So the inverse of a pair of elements is given by the pair of the corresponding inverses. Yeah. If you want to have a closer look, just pause the video and read along the formula here. And of course, we can generalize this construction to products of more than two groups, so we can form group products with an arbitrary amount of groups, G1 up to Gn. Now we come to some very basic properties, but very important properties of groups as well, that distinguish them from more general algebraic structures. And these properties are, in the end, what make groups so useful. First, we prove that the neutral element is uniquely determined by the group laws. So how do we do that? We suppose there is another element, E prime, in the group G that has the same properties as the neutral element, and then we conclude that it has to be the neutral element already. Suppose E prime satisfies E primes times G equal to G, and this is the same as G times E prime for all the elements in the group. And then I claim this E prime is already the neutral element. So there can be no distinct second element with these properties. Let's prove this. So E is the neutral element. So by definition, that means E times E prime equals E prime. Now we use our assumption on E prime, where we plug in the neutral element for the element G here, because it holds for all G. So in particular, it holds for the neutral element. So we get E is equal to E times E prime, but here we just had that E times E prime is E prime. So if we take this equation and this equation together, we find that E is equal to E prime. This may seem very trivial, but you have to think about it carefully, and you really have to use the group properties and the properties of the neutral element to come to this conclusion. And a similarly subtle proof is the proof that the inverses of an element are unique, or the inverse is unique, I should say. So suppose we're given an element G in our group, and there's some element G prime that satisfies G times G prime is the neutral element, and G prime times G is also the neutral element. Then this G prime has to be the inverse element of G. So there can be no two distinct elements that behave like an inverse. It has to be the unique inverse in the group. And to prove this, we recall that G inverse means that E is equal to G times G inverse. It's just by definition of the inverse element. And now we can write G prime as G prime times neutral element by definition of the neutral element. We can write the neutral element like this. So this is G prime times G inverse. Now we use the associativity to write this as parenthesis G prime times G inverse. Now we use the assumption that G prime times G is equal to E. So we replace this by the neutral element. But neutral element times G inverse is just G inverse, and we find that overall G prime equals G inverse. Again, this might seem like we're just doing something trivial here, but no, you actually have to carefully apply the group properties to come to this uniqueness of the inverse. As an exercise for you, some more properties of inverses. So pause the video for a few minutes and prove the following. G is a group. We have two elements, G and H, in our group. And first you should prove that the inverse of G inverse is G itself. And second, you have to prove that the inverse of the product GH is the product H inverse times G inverse. So you reverse the order here and take the inverses. For a solution, for the first case, note that G satisfies G times G inverse is equal to the neutral element, and this is equal to G inverse times G. So yeah, the element G just satisfies the properties for the inverse of its own inverse, and therefore the inverse of the inverse is the original G. It can't be any other element because we've just previously proved the uniqueness of the inverse, and that means we're good here. And for the second one, look at the following. We multiply the product GH by the right-hand side here, and because we have associativity, we can regroup these elements like this: G times H inverse times G inverse. This is the neutral element, so we can just delete this. Then we're left with G times G inverse, which is also the neutral element. So this satisfies the property of this inverse here from the right. And in the same way, pretty much you can show that it also satisfies the property of the inverse from the left. And again, by the uniqueness of the inverse, this shows us that this here is indeed the inverse of the product GH. Another important property when we want to perform computations in groups is the cancellation property. This states that for all elements A, X and Y in a group G, we have that AX equal to AY implies that X is equal to Y. So we can cancel the group element A. And this is the same just from the other side. So X times A equal to Y times A also implies X equal to Y. For a proof, let's look at AX equal to AY. Then we can multiply both sides with A inverse, and because we have associativity, we can group the A inverse and the A together. Those two cancel out because this is the neutral element, so we're left with EX equal to EY, but because E is the neutral element, this is just X equal to Y. So we've seen by a few equivalent manipulations that this is equivalent to this. And the second one we can prove along the same lines. And another important property of groups is the unique solvability. It's a bit similar, but not quite the same as the cancellation property. So for fixed elements A, B in the group and some unknowns X, Y, there's a unique solution for each of these two equations. So there's a unique solution to AX equal to B, and there's a unique solution to YA equal to B. We'll just prove it for the first one. So by multiplying A inverse from the left of this equation, we find that AX equal to B is equivalent to A inverse times A times X equal to A inverse times B. Again, these two cancel out because they're the neutral elements. So this, or the original equation, is equivalent to X equal to A inverse times B. So this would be our unique solution here. Very similar, we do it for the second equation here. We would find that Y equal to B times A inverse is the unique solution of the second equation. Now let's have a look at subgroups. Recall from our initial examples, the symmetries of the circle and the symmetries of the triangle, that both of them are groups in their own right with the same operation, namely the composition of maps. But here the second group is included as a subset in the first one. And this is actually a quite common phenomenon, and it is often helpful to identify a set with an operation as being included in a larger group so that it can inherit the group properties from the larger one. And for this we make the following definition. So if G with this operation circle is a group and S is a subset of G such that S together with the same operation is a group as well, then we call this S a subgroup of G. And sometimes you will find the notation S less or equal G to express that S is a subgroup of G. Personally, I don't like to use this notation because it's not always clear, maybe not everyone is familiar with it, so I prefer to write it out explicitly that S is a subgroup of G. As our first example, we already had it, the symmetries of the triangle form a subgroup of the symmetries of the circle. Of course, assuming that this triangle lies on the circle. The vertices of the triangle lie on the circle. Another, maybe now more interesting example, because it's new, is the set of even numbers, which I denote by 2z. So this is the set 2 times x for any integer x. And this, I claim, is a subgroup if we take the usual addition of the integers. Let's verify this. So first we need to check that that 2z is closed on the addition. So if we have two even numbers, a, b, that their sum a plus b is again even. By definition, a and b being even means a is equal to 2x and b equal to y for certain integers x and y. And hence, if we look at the sum, a plus b, this is 2x plus 2y. We can factor out the 2, so this is 2 times x plus y, and x plus y is again an integer, so this is indeed an element of 2z. So the even numbers are closed under addition. Clearly they contain the neutral element 0, because 2 times 0 equals 0. And for each element a that is even, its negative element minus a is also even, of course. And this proves that 2z is indeed a subgroup of z. And in fact, the same is true for nz for any integer number n. So if instead of 2, we replace the 2 by some integer n here. So the multiples of any integer number n form a subgroup with respect to the integer addition. And recall from one of our previous exercises that we had this subset of the permutation group on n numbers. So we proved in the exercise that this set is a group, sigma contained in the permutations on n numbers that satisfy that they fix the element 1, so they map 1 to itself. And because we already found that this is a group, it is in fact a subgroup of Sn. And this subgroup is called the stabilizer of 1, simply because it stabilizes the element 1. None of its elements actually permuted to some other element. And so you don't have to verify all the group properties every time you want to check that some given subset S in G is a subgroup. You can use a very convenient criterion to show that something is a subgroup. This goes as follows. Let G be a group, and we're given some subset S of G. And this is a subgroup of G if and only if the two following properties hold. Firstly, S is not empty. And second, for any two elements GH in the subset S, the product G times H inverse is also contained in S. And if these two hold, then S is indeed a subgroup. For the proof, because we want to prove an equivalence if and only if, we first assume that S is a subgroup and prove that these two properties hold. So if S is a subgroup, it's a group, of course. Then it's not empty because the neutral element has to be contained in S. So we can tick the first box. And if it's a group, the inverses are contained in S, and it is closed under the group operation. So that means for any elements GH in S, of course, G times H inverse also has to be in S. The other direction, we now assume that the subset S satisfies these two properties and will conclude that it has to be a subgroup. So first we use the first property, S is not empty, so there must exist some element G in S. And now if we apply the second condition to G with itself, we find that G times G inverse has to be contained in S, but G times G inverse is just the neutral element. So we find the neutral element has to be contained in S. Now that we know this, we can again use the second condition with G replaced by the neutral element. So we find that G inverse for G in S is the same as neutral element times G inverse, but we know the neutral element is also an element in S. So by this property here, we find that this product, namely this element here, has to be contained in S. And this shows that for any element G in S, the inverse is also contained in S. Finally, we check that S is closed under the group operation. So we take any two elements G and H from S and want to show that the product is again in S. Now we know from what we just shown here that for H, the inverse is also contained in S. So we can write H as H inverse inverse. And now we use the second property here for H replaced by H inverse to conclude that this is an element in S. So in other words, the product of any two elements from S is again in S, and that means S is closed under the group operation, and thereby with all three together, E being contained in S, the inverse is being contained in S, and S being closed under the group operation, it has to be a subgroup. That concludes our proof. Let's look at some more examples. Again, I use the hollow letter K to denote any of the rational numbers, the real numbers, or the complex numbers. And we'll look at another matrix example. So here I define the set SLN of K to be the set of n by n matrices A whose determinant is equal to 1. And I claim this is a subset of the general linear group and indeed a subgroup. Recall this one was the set of matrices whose determinant is different from 0. So clearly if the determinant is 1, it has to be contained here, so it's obviously a subset. But we also want to convince ourselves that this SLN is a subgroup. First, we check that SLNK is not empty because the identity matrix has determinant equal to 1, so it's contained here. And for two matrices AB that are contained in the set SLNK, we observe that the determinant of B inverse is just the inverse of the determinant, and if B has determinant 1 to begin with, then of course its inverse will also have determinant 1. Using the subgroup criterion, determinant of A B inverse is by multiplicativity of the determinant, det A times det B inverse, which using this and the assumption on A and B is 1 times 1 equal to 1. So it follows that A times B inverse is also contained in SLNK if A and B are. And now the subgroup criterion with these two properties here tells us that SLNK is indeed a subgroup of GLNK. And this SLN stands for special linear group. So recall the GLN was the general linear group, and here the SLN is the special linear group, which is a subgroup of the general one. Next example, let's look at the vector space K2. So here we have vectors with two entries, which are taken either from the rationals, the reals, or the complex numbers. And this is a group with component-wise addition. We know that from our group product theorem that we proved just a few minutes ago. And I say that any line passing through the origin is a subgroup of this group here. Now first, what do I mean by such a line passing through the origin? I take any non-zero vector v, and then I look at all the multiples of this vector. So I take all the numbers alpha contained in K and multiply them by this fixed vector here, and all the vectors I get by doing that form my line L through the origin. Now I apply the subgroup criterion to show that this is indeed a subgroup. So first of all, it's not empty since the origin lies in L. So I pick the element 0 here, multiply 0 times this vector, so I get the 0 vector, which is the origin. This is contained in L, so L is not empty. Now I take two vectors x, y on L, so two vectors lying on this line L. That means x is equal to alpha times this vector v, and y is equal to beta times this vector v for certain numbers alpha and beta. And then I look at the difference. So I take x plus the inverse of y, and this is just alpha minus beta times v. So this is just another number that I could multiply v with, so this also lies on the line L. So by the subgroup criterion, it follows that L is indeed a subgroup of this vector space K2. Now you can study some non-examples of subgroups. So pause the video for a few minutes and prove that these two are not subgroups. First, look at the subset of odd numbers in the integers. So I call this x, and the odd numbers are given by 2n plus 1, where n runs through all the integers. So you get an even number plus 1 has to be odd, and the totality of those makes up the odd numbers. The second example is a line j that is not passing through the origin in this vector space K2. And this j is defined as follows. Again, we take two fixed non-zero vectors v and w. And again, for v, I just run it through all its multiples, where I have this factor alpha that can be any number from this set K. And I offset this line here by this vector w. And in order to make sure it doesn't go through the origin, I have to assume that v and w are linearly independent. So in other words, w is not a multiple of v. the solution is as follows. For the first one, you have multiple ways to show it. So the most direct one is probably to just say that the neutral element 0 is not an odd number. So there's no way to write 0 equal to 2n plus 1 for any integer n. So 0 is not contained in the odd numbers. Alternatively, you could prove that the set of odd numbers is not closed under the addition, because the sum of any two odd numbers, as you can see here, is an even number. So these are two things where the subgroup property of the odd numbers would fail. And as for the second one, the lines not passing through the origin, so since v and w are not multiples of one another, there's just no way to combine alpha v plus w to become the zero vector. So for any choice of alpha you pick here, you would never get the zero vector. So the neutral element of the addition is not contained in this line j, and therefore it cannot be a subgroup. And there's another exercise for you. Here you prove that if G is a group and we have two subgroups of G, S1 and S2, then the intersection of those two is also a subgroup of G. We use the subgroup criterion again. First, we observe that the neutral element is contained in the intersection, so the intersection is not empty. Why is it contained in the intersection? Because, of course, it has to be contained in each one of the two, S1 and S2, so if it's contained in both, it is contained in the intersection. Now we take x and y that are contained in the intersection, and that, of course, again means that x and y are contained in both S1 and S2. So by the subgroup criterion for S1, x times y inverse is contained in S1, and also by the same reasoning, x times y inverse is contained in S2. But if x times y inverse is contained in both, then it's contained in the intersection, and that concludes the proof. By the subgroup criterion, the intersection is not empty, and it satisfies this property for all xy in the intersection. And here we have a theorem that generalizes the previous exercise. So let G be a subgroup, and here we have a family of subgroups that is indexed by some index set, and then I say that the intersection over all of these subgroups is again a subgroup of G. Now this may be a bit confusing from the notation. What I mean by this is basically that this index set can be any set. Finite, infinite, countably infinite or uncountably infinite, anything you like. And what this basically says is only that you can take any number or any amount of subgroups in G, and the intersection will always be again a subgroup in G. And the proof is basically the same as the previous exercise. So first you check that the neutral element is contained in the intersection because it's contained in each individual subgroup, so it's not empty. And then you remind yourself that by the subgroup criterion for each of the individual subgroup, the product x, y inverse is contained in each individual subgroup, and hence it must be contained in the intersection. And you can apply the subgroup criterion to find that the intersection is a subgroup of G. Now we introduce a new concept for subgroups, and we do this because throughout this course we will find that subgroups often allow us to gain a deeper understanding of a group as a whole, and the importance of these concepts will become apparent later on in this course. So I will just introduce them here now so you're familiar with them, and we will keep using them later on in the course. Let G be a group and S a subgroup of G. Then for any element G in the ambient group G, we define the left coset, written GS, of the subgroup S to be the set that contains all products GS, where S, little s, runs through all elements of the subgroup S. And analogously, we define the right coset, big S times G, as the set of all products SG, where little s runs through all the elements of the subgroup S. Now we observe that if G is an abelian group, so a commutative group, written additively, so with a plus as the group operation, then left and right cosets are identical. So G plus S and S plus G are the same set for every element G in the abelian group. That is clear from the definition. If the group is abelian, we can just switch the order of G and S here, and then these two sets are identical. And indeed, these cosets form equivalence classes for a certain relation. So let G be a group, S a subgroup. And then we define this relation tilde L, which I define here. G and G prime are related if they have the same coset. So GS is the same as G prime S. And I claim that this is in fact an equivalence relation, where the left cosets GS are the equivalence classes. Moreover, if two elements G and G prime are equivalent by this relation, then they differ only by a multiple in the subgroup S. So G is equal to G prime times S for some element from the subgroup S. And of course, a corresponding statement holds for the equivalence relation induced by the right cosets, but I will only focus on the left cosets. We will prove that it is an equivalence relation, this one here. First, we have to show that it's reflexive, so that G is related to itself. But this follows directly from the definition. So of course, GS is equal to GS. If I replace G prime by G here, so this is trivial. Also, symmetry is clear because G being related to G prime implies G prime being related to G, simply because the equality here is a symmetric relation. So GS being equal to G prime S is of course the same as G prime S being equal to GS. So there's nothing really to do here. Transitivity, so we assume that G1 and G2 are related and G2 and G3 are related. By the first one, this means G1S is equal to G2S. The second one means G2S is equal to G3S. But if G3S and G1S are both equal to G2S, then of course this means that G1S is equal to G3S. So G1 and G3 are related as well. This shows that we have an equivalence relation. And to prove this one here, well, first we note that the neutral element is contained in the subgroup S. So both G and G prime are contained in GS if they have the same coset. And G is contained in G prime S, which is the same as GS. Then, of course, by definition of the coset G prime S, this means G is equal to G prime S for some element little s in the subgroup S. Here I have a schematic image to illustrate the properties of coset a little bit. So suppose this is our group G, and the dots are all the elements in G, and the blue ones in particular are the subgroup S. And here we have our neutral element, which has to be contained in the subgroup, of course. Then we obtain the coset GS by multiplying all the elements of S with this element G. In particular, G itself is contained in the coset because the neutral element multiplied by G gives just G itself. And if we have two elements G and G prime that are equivalent, that produce the same coset here, then we get the same elements, the red ones, multiplying all the blue elements, the elements of S, by an element G prime. But of course here every element of S might be mapped to a different element than we would map it to if we multiply by G. And G prime are related by some element S, so this would correspond to multiplication of E with some element S from the subgroup S, and G and G prime being both contained in the same coset means they are related by such an element little s from the subgroup S. And here we have the situation that we have elements G and G prime that are not equivalent, and so they produce disjoint cosets. There's no intersection between the green ones and the red ones here. We'll explore the properties of cosets a bit further. So let G be a group with subgroup S and tilde the equivalence relation for the left cosets of S, so the one we just studied. I just dropped the index L. And by R, I denote a set of representatives for the equivalence classes of this relation. That means from each coset GS, I pick precisely one element of this coset. Okay, so maybe going back to this image here. So for each coset, the red one or the green one, I pick precisely one element, say this one or this one here for each coset. And these together make up this set of representatives. And it doesn't really matter which elements I pick. And then my theorem 28 states that I can partition my group G into cosets. More precisely, it says that for any two elements G1, G2 in the group G, I have either G1S equal to G2S, so either the cosets are identical, or the intersection of the cosets is empty, so they're disjoint. And as a consequence of this, G is a disjoint union of left cosets. So G is equal to the union of the cosets, GS, where I take the union over the representatives for each coset. So each coset appears exactly once in this union here, because I have only one representative for each coset. And this is a direct consequence of this property here. And of course, the analogous statement holds for right cosets. Now, in principle, this is just a property of equivalence relations, but I still want to give a proof here so we get a little bit more practice doing group computations. What we have to prove is that either two cosets are identical for different elements G1, G2, and G, or their intersection is empty. I assume the intersection is not empty, and then I have to prove that this situation here holds. Okay, assume the intersection is not empty. Then there is an element in the intersection of these two cosets, and I can write this element in two ways, as G1, S1, because it's contained here, but I can also write the same element as G2, S2, because it's contained in here. Now we consider any element G1S contained in the coset G1 times big S, and I want to prove that this is contained in the coset G2S. Since S is a subgroup, there is some element S prime in this subgroup such that this element S here can be written as S1 times S prime, where S1 is the element here. And this is true by the unique solvability property that we learned before. But then G1S is, if I plug this in, the same as G1 S1 S prime. And now I can replace G1 S1 by G2 S2 here. So this becomes G2 S2 S prime. But S2 S prime is just an element of the subgroup S, so this is contained in G2S. So I've shown that any element of G1S is contained in G2S, so G1S is a subset of G2S. But I can just reverse the argument for an element from G2S and show that it's contained in G1S, and that means the two sets, G1S and G2S, have to be identical. And that proves this theorem here. The next theorem is about an interesting way to produce new subgroups out of a given one. Namely, if G is a group and S is a subgroup, and we have any element G in the big group G, then the set G times S times G inverse is a subgroup of G as well. So this just means we take the set that we get by taking any element of S and multiplying from the left with G and from the right by G inverse, and the totality of all these elements gives you this set here. And I claim this is a subgroup of G as well if S is a subgroup. And then we call this subgroup GS G inverse the conjugate subgroup of S by the element G. Let's prove this. We know that the neutral element is contained in S, but the neutral element can be written E as G times E times G inverse, because the E here is just redundant. We can omit this, then we have G inverse, but this is just the same as the neutral element. So we see that the neutral element is in fact contained in this conjugate here. And this means the set G as G inverse is not empty. Now look at any two elements x1, x2 contained in the conjugate here. Then by definition of this means there exists two elements S1, S2 in the subgroup S, such that Xi is GSI G inverse, where I is either 1 or 2. Now S is a subgroup, so S1 times S2 inverse is some element S contained in the subgroup S. So let's try to apply the subgroup criterion on these two elements here. So we look at the product x1 times x2 inverse, and we plug in these expressions here for x1 and x2. So for x1 we get G S1 G inverse. For x2 we get G S2 G inverse and take the inverse of all of that. If we do that, we get G S1 G inverse, G S2 inverse, G inverse. The G inverse and the G here cancel out. So we're left with G S1 S2 inverse, G inverse. But from here, because S is a subgroup, we know this is some element S. So this is G S G inverse, and this is again contained in G subgroup S G inverse. So this shows by the subgroup criterion that G S G inverse, the conjugate, is indeed a subgroup of the group G. Let's look at an example for such a conjugate subgroup. So we go back to our triangle symmetry group again. And the symmetry group of the triangle has a subgroup S consisting of just two elements, the identity, and one reflection across the axis L0. Here we have them visualized. So the identity just doesn't do anything. So here we have our vertices 1, 2, 3. The identity doesn't do anything to them. And the reflection SL0 fixes the element 1 because it's just on the reflection axis, and it flips elements 2 and 3. And now let's look at the conjugate of this subgroup. Namely, we conjugate S by the rotation G, which is the 2/3 rotation. So 4 pi divided by 3 rotation. What we get is GS G inverse, which is again a subgroup with two elements, the identity of course, and then we have G composed with the reflection sigma L0 composed with G inverse, and you can check that this is indeed the reflection across the axis L1, which is this one here. So the original subgroup consisted of the identity and the reflection across this axis, and the conjugate subgroup, if we conjugate by this rotation, consists of the identity and the reflection across this axis here. And if you don't believe this, I invite you to verify this yourself by identifying the symmetries of the triangle with the permutation of the vertices, and then just checking these properties by using the permutation representation. There's a particularly interesting class of subgroups, and those are the subgroups that are invariant under this conjugation operation. So if G is a group and N is a subgroup of G, such that for all elements G in the group G, it holds that G n G inverse is equal to N itself, then we call N a normal subgroup of G. Evidently, in an abelian group, every subgroup is normal. Again, this follows by just checking if you have G times some element N times G inverse, you can just switch the position of N and G inverse, then the G and G inverse cancel out, and all that remains is N. And we have the following proposition about the cosets of normal subgroups. So a subgroup N of group G is normal if and only if for any element G of the group G, the left coset and right coset are identical. So Gn is equal to Ng. And for the proof, we observe that Gn G inverse being equal to N is equivalent to those two properties here. Firstly, for all N in the subgroup N, there exists some N prime such that Gn G inverse is equal to N prime, meaning that this part is contained here. And second, for all N prime in N, there exists some N prime prime such that Gn prime prime G inverse is equal to N prime, meaning that this part here is included here. And 1 and 2 together just mean that they are identical. But this is equivalent to, for all N in N, there exists N prime in N such that, manipulating this expression, Gn is equal to N prime G, which of course is contained in big N G. And second, for all N prime in N, there exists N prime prime in N such that N prime G is equal to G N prime prime in Gn. And together 1 and 2 become that Ng is equal to Gn. So this is equivalent to this. Let's finish up with an example of a normal subgroup, one that we've already seen. So recall the special linear group SLN consists of those n by n matrices S with determinant S equal to 1. And I claim this is a normal subgroup of the general linear group. We already saw in an example before that it's a subgroup, but I claim it's even a normal subgroup. And to see this, consider any matrix G in the general linear group and any S from the special linear group. Then the determinant of GS G inverse is by multiplicativity of the determinant, just determinant of G times determinant of S times inverse of determinant of G. And because this and this cancel out, this is just the determinant of S, but determinant of S was equal to 1. So this matrix here has determinant 1 if S has determinant 1. So this means GSG inverse is contained in SLN for every element S in SLN, and this proves that SLN is a normal subgroup. And that's it for today. Thank you very much for your attention. Please help me generate my subscriber group, by which I mean like this video and subscribe to my channel, and tell all your friends about my awesome videos.